Hi guys. In the previous class, we were just on this point where we were talking about the Mao Palace case study, and we were talking about the most important parts of the output of the linear regression. The first part is the R square or adjusted R square. R square is the measure that we concerned about when, or we take into consideration, in fact, when we're talking about a simple linear regression with only one independent variable. And this is the case. We have the price of the ball as an independent variable, and we have the number of balls sold as a demand function. And now we explain that this is more or less an explanation of the model, how much it explains the total variance in the dependent variable. Or if we have a simple linear regression, it does make sense that we just mention the name of the variable for simplicity. So in simple linear regression, we say the price of the rice bowl explains, for example, here, explains 50, let me just take it here, explains 0.67% of the total variance in the number of balls sold. What about the 50%, the other 50%? Who's responsible for it? Other variables are responsible for the variation, the other 50% variation. Okay. The second very important part indeed is the standard error. The standard error here is resembles the standard deviation in a normal distribution. If you need to go over your statistics course, your statistics book, please take a look at the normal distribution and how 68% of all the points of a data set, normal data set, will lie in within one standard deviation, while 95% of the normal data will lie within two standard deviation. For this purpose, we use the standard deviation in general as a threshold to test and check for outliers. Having this said, the standard error is basically the standard deviation for the error term. So what we did is we took the absolute residuals. We basically, in the output, we have the predicted balls and then we have the residuals. I like to actually cut the residuals, shift them a little bit, and then in that place put the absolute residuals and not after the residuals. And I have a point why to do that, and you will see in a bit. So over here, we got the absolute error so that we can easily check if this absolute error is less than or equal to these two standard errors, which is over here. We have it as the 2 times Q8. Q8 here is the standard error. So basically, you need to make sure that you also add the dollar signs before the T, which is the column, and before the number of rows, which is here 25, so that you freeze the reference of that cell, and basically double click on the corner to copy all the equation all along. Now we need to check if 95% minimum of the data points lie within two standard errors. So we take the sum. The sum is basically we signaled 1 whenever the point in fact lie within two standard errors or below two standard errors, and over the number of observations here, 186. So here we got 100%, so we have it's true. So we can write here for the standard error a total of 100% of residuals lie within two standard errors. So we have no outliers. So there's no outliers in the data set. What is an outlier? An outlier is a data point in the data set that is distant, far away from other points in the data. For example, if we have a point here that is higher than the other observations, or if we have a point here that is lower than the other observations. For example, if we had a very horrible bad weather and people were not going to offices and so on. So maybe I haven't sold that much of, maybe it is not really at the lowest price, let's say. Yeah, or maybe at the lowest price, even though we know at the lowest price we sell probably more, but we didn't sell that much. It's an outlier. Maybe the weather was different. So we need to say that all these interpretations that we are saying, especially the interpretations of the coefficients, are an interpretation having all other variables constant. So with all other variables constant, this is how this variable is affecting the y variable. All right. Now, what we are trying to say here, this is an outlier because it is distant from the average, from the density. You see how dense the points are? We have a high density over here. When we have certain points like that, they actually represents outliers because they are distant away from the density, from the core where all the data points are clustered together. These outliers, usually you look at them in a negative connotation. You say, oh man, I have outliers. God, I have to clean the data. This is how you look into it because you are a data analyst. You have to finish up the data cleaning very quickly for your senior data. You actually is a data. They can call you as a senior data analyst, or just an associate data analyst, or assistant data analyst, or a data steward. I think most companies, they will call you at the very early 2 years of your life as a data steward. A data steward will always just clean the data, make it nice and beautiful for the data analyst. However, I feel that it is of a paramount importance if you're doing a project that you have to present and I tell my students, my master students, when they're doing their thesis, even my bachelor students, if they're doing thesis based on data sets, I tell them I need to see in the presentations the list of outliers. And also, why do you think this was an outlier, if you can? Now, if you're working with a certain organization and you are the manager, these outliers will be a very important part of your life, and you should understand what kind of conditions produce these outliers, so that you can adjust the purchase, for example, of materials. So if that was a snowy day in the downtown, snow days, we're not going to have many balls sold, for example, in our shop, but maybe delivered, for example. And so you can use this kind of information either to avoid it, or you are cooking with a certain ingredient, and you because of that you have experienced a drop in sales. So you can avoid this kind of conditions that produce these very low outliers. But on the other hand, you can also understand what kind of conditions led to producing these very high outliers, so that you can, if it's under your control, so you can reproduce them. Then let's say that you had a festival in the downtown and this has increased your sales. If you can work with other restaurants around you in the same street and say, you know what, we're gonna have in this month we have very low sale. It is maybe we are all around the university and it is a summer vacation. Let's pop up something called whatever festival over here. With the help of the students, we're gonna reduce prices a little so that we can sell more. So maybe you can have you can benefit from the conditions, understanding the conditions that led to producing these outliers. So what I'm trying to tell you here, that we need to check for outliers because outliers can, because we're talking about residual and distance from the line. Remember, how do we fit the line? We have endless lines, and the system chooses only one line, the line that that minimized, or the line that satisfies the rule that the distance between all the actual and the predicted points is kept to the lowest, meaning all the absolute residuals or the squared distance of residuals is to the minimum. Now, if you have this point over here or this point over here, this will actually affect the slope of the line. So it might be tilted a little bit down or tilted a little bit up. This might pull the line up, this might pull the line down. And it's just because we have only one point, not all the points. So this affects the model. So this is why we get rid of outliers mathematically. Mathematically, we don't like them, we want to get rid of them. But if you're a manager, you really need to understand what brought about these outliers so that we can understand how to reproduce these conditions. Either avoid or either reproduce these conditions to get more sales, right? So I want you to in-depth understand the outliers, not just follow the steps one by one. All right, so it is very good that you, as a steward, shows the list of outliers first below and the list of high outliers, so that you can in the visualization, and then you can also, if you have time, you can try to investigate why this has happened. All right, very good. So now all the data is within two standard errors. We don't have any outliers that can pull this line up or bring it down. Everything is okay. There is no inflation here and there. Now we go to step number 3. And in step number 3, what we really want to take a look into is, does the model, all the variables in the model are very important in explaining the variance, all the significant variables. So here you want to less than 0.05. If this is less than 0.05, we reject the null hypothesis. Null. What does null mean? Null means empty, nothing, negation. Negation means that this model, the components of this model, here we have only one component, independent variable. I told you that the main components of the model that we look into is the independent variables. I know that there is a constant, but we are more concerned of the independent variables. So basically, the model here says when the F significance here, it says the hypothesis, the null hypothesis, the hypothesis that has nothing in it, it says basically this model, the components of this model, or all the independent variables in this model have no effect, has no real effect on the dependent variable. So we always look for the alternative hypothesis. We hope that we reject the null hypothesis. So we say we reject the null hypothesis. Thus, sorry guys, sorry. Thus, all independent variables, in this case we have only one independent variable, right? All independent variables in the model are important, basically. It's in the simplest way possible. All right, so this is number 1, number 2, and number 3. Now we come into looking at the p-value, so that we can see if these coefficients should be taken into consideration. First of all, let's take a look at the equation. Y is equal to let me see if I can put it in a fancy way here. y is equal to the intercept here and minus this one, x. Isn't that correct? Y is equal to the intercept, 695 volts, basically, when the price is 0, minus 29.5x, which means here, this is the number of sold balls, or of balls sold, it's better, is equal to 69.5.87 plus, actually minus 29.59, and x here is the ball price. Okay, so this is the linear function. All right, so over here comes number 4, the most important part here. One of the next very important part here is number 4. Number 4 is basically investigating these p-values. All the p-value here, value is supposed to be less than 0.05 so that it is significant. And I think this is something that you talked about a lot in your statistics course. So over here, we're going to say, all right, this is okay, and this is okay. So I'm going to highlight these for you and put them in green light. This means that they are just great. They are less than 0.05. So they are, sorry, this is the intercept. As I said in class, we don't take a look at the intercept, right? If you have caught this before me, good, you are focusing in class. So we only look at the independent variable. So here, this independent variable, and we have a simple linear regression, we have only one variable. So this independent variable has a significant p-value, and this p-value is less than 0.05. Very good job. This means that I can proceed by interpreting the coefficient. However, I do not like to interpret the coefficient before I go over the main assumptions of linear regression, because this coefficients and this p-values means nothing if the model did not meet its assumptions. So right here, the p-value, even if significant, is not valuable unless it meets, unless linear regression satisfies its assumptions. So linear regression has multiple assumptions, and they are as follows. 1, the normality of the error terms. The errors needs to be normal. So we need to check for normality of the error term, and usually we check for the normality of the error term based on skewness and kurtosis. All right. I have to admit that whenever you have a continuous data, we focus more on the skewness. But if you're having a questionnaire data, which is not continuous data, your focus is more on the kurtosis, because skewness is inevitable, and especially if you have a 1 to 5 kind of data. Now you will tell me, but how is the residual might be normal? Well, this is a different this is a different discussion, because sometimes you can deal with the ordinal data as linear data if it satisfies certain conditions and it's getting normalized in a certain way. But I still deep inside feel that this data, kind of like Likert scale data, or the right way to call it is not Likert scale, but rather anchored scale data from 1 to 5, 1 to 7, will never be normal. And if you have the choice of using techniques parallel techniques for non-normal data, for this kind of data, I'd rather use it for validity of the results and validity of the research. So I resort to first of all alternative methods to deal with kind of non-normal data without having to deal with techniques that like linear regression that deals with the normality assumption, because this kind of data, if it's not continuous, it will never be normal. So this is linear regression works best for normal data. Okay, so normality assumption is not for the data itself, it's a normality of the error term. So if the data itself is not normal, it's even more difficult for the error term to be normal. So normality of the error term, and then we talk about the assumption of homoscedasticity, and I think today we talked about the homoscedasticity. In some books you will see something called the heteroscedasticity check. So this means that I'm checking for the bad, for the heteroscedasticity. But in other books you will say homoscedasticity assumption. So let me write it here as homoscedasticity assumption, or heteroscedasticity check. Okay, now this is, let me put normality assumption so that you know we're talking about assumption. Okay, and multicollinearity assumption. The multicollinearity assumption is basically making sure that these variables are not highly correlated and they are independent from each other, just as the name indicates. Also, this means that they are not redundant. Now, for example, Nora collected data from her research on your monthly spend and on your monthly spend on online shopping. And she wants to use a percentage of your monthly spend on online shopping, and that is over your total monthly spend. So that's a percentage is based on other two values. This percentage will be highly correlated to both. Will be this percentage, the rate of online spend over total monthly spend, will be highly correlated to both variables, the online monthly spend and the total expenses, monthly expenses or monthly spend. So in this case, you need to make sure that you either use the variables as is, or sometimes the variables are not giving us very good results, but maybe the ratio might be significant. So maybe the variables, this is why the reason why we come up with ratios sometimes. First of all, because we don't want to disclose the privacy of our participants, and this is something I do all the time. I don't like to put out there the minimum, the maximum of the income of our students, especially if we collect the data, or how much they spend online exactly. I keep it for myself, but I can disclose the percentages, how much percentage you spend from your total monthly expense or on online shopping. The most important part is to understand when do we use it. Sometimes you are forced to use this kind of rates and percentages because maybe you know that these variables are very important in your model, but they don't end up being significant. So you do the percentages, maybe the percentage will be very much significant. Then you get rid of the other variables and you just use the percentage. So I'm telling you little tips and tricks when you are working with the data and building models that's supposed to hopefully be stable and consist of all independent variables being significant. All right, lovely people, let's begin. So we're going to start with first the normality assumption. So this first is nothing but number 5. Okay. It's gonna give me a headache. So number 5 is normality assumptions or assumption of error term. All right, the normality assumption of error term, we take the skewness here and we take the kurtosis. Sorry. We take the skewness, and we take the kurtosis. How do we find the skewness? Basically, we take the skewness, which is the skew function in Excel of the residuals, not the absolute residuals, the residuals as is, and we hit OK. And the same applies to kurtosis, even though, as I said earlier, with which is court for continuous data, we're more concerned with the kurtosis, the skewness. Now, I had a very nice. Did I have it here for you? I think I should have it somewhere. Oh, I don't have it. I have a table. I don't have it here. That is really sad because I do have it maybe here. Yes, it's right there. So if you go to 4, Regression Analysis Tool Pack, you will find this table. This table, we usually use it for very small data points. So basically, over here, when we have samples, very small samples, so we need to use certain numbers of skewness and kurtosis. But once the sample is 100 and above, then the variations becomes very trivial. So basically, we take these readings. For our sample, we have how many observations? We have 186, so it's over 100. So we're going to take roughly these readings. But in general, skewness and kurtosis, basically, there's tolerance zone. Some say for skewness we can tolerate anything between 2 and -2. As you can see here, we have 2.5, as a skewness. This is the lower bound, this is the upper bound, and over here this is the lower bound, this is the upper bound. But in general, let's just follow these ones. So it is in between 0.48 to 0.46. We can see that this reading is in between. And over here it is 0.71 and 1.13. So this one also a little bit doesn't lie in between, but it is okay since the skewness lies in between. So we can say here we see no concerns. So we say there is no serious concerns regarding the normality of the error terms, because the skewness is fine, and usually the normal distribution has a kurtosis of 3 and -3. So this is the tolerance zone. So if the kurtosis is in between 3 and -3 is okay. Skewness is in between 2 and -2. Some people say it's okay. If you want to be more strict, you can take a look at this table. But in general, also, this is just very good readings. We're gonna switch now to the second assumption, which is the assumption of heteroskedasticity. But let me not make the video too long, and let me meet you again in the next video where we're going to discuss the heteroskedasticity check or the homoskedasticity assumption and the multicollinearity assumption. So in the next video, I'll see you again to talk about the homoskedasticity assumption and also the multicollinearity assumption or check. Thank you so much. See you in the next video.